Think Forward. Think Research Channel.
I thought about titling this talk, How to Replace Your Mother-in-Law, but there are a couple of flaws with that. My wife Jerry is here, and I have a mother-in-law who's practically a saint, so that's very difficult to begin with. But also, I think that's already happened. We test drove a car a couple of months ago that has one of these navigation systems in it, and as soon as you pass your turn, it starts saying, you've made a wrong turn, go back 1 mile. So I think that's already happened, but we are moving in the direction of automating the driving process. And this talk is a mix of some lighter information, but also some technical information. And if you have questions, I should talk about 25 minutes, and then there should be a few minutes for questions at the end. You probably wonder how I got asked to talk today, and if you saw the paper yesterday, maybe it'll be obvious. And I'm sorry, I'm walking in front of the screen. I didn't bring a wireless remote. Big names, big bucks. Yep, they got me here. Today. It was perfect timing on the article. I'd like to go through first of all some definitions and just give you some background. I know there are some people here. There are a number of my students are here, and thanks a lot for that. And I know many of them are way ahead of me in a lot of these topic areas, and so maybe they're going to be the ones answering the questions. But I would like to give some definitions to the people who aren't real familiar with autonomous vehicles and this whole subject area. Then I'd like to talk just a little bit about the motivation for studying this topic. I think that's important, but we could talk all day about that. And then just tell you what autonomous vehicles look like, what kinds of equipment we're putting on these things to make them autonomous. Then we really get into some of the tough problems we don't have at all time to even begin to scratch the surface on, things like perception and cognition and all the fun things to talk about, the really tough problems. And I also want to go through and show you some of the things I'm most proud of, the student projects that we're working on here, and some of the research and how that ties together. And then there are a lot of unanswered questions and opportunities, and I'd like to talk about that a little bit too. This is an example. The video you're seeing is an example of something that we call a teleoperated system. And so you probably heard some words thrown around, unmanned system. And if you watch as the video zooms in, you'll see that there's no driver in the cab of this 16-ton excavator. The driver is sitting about a half mile away looking at that video screen. So the driver, you'll see in just a second, Troy, works for the Navy at Dahlgren, and they're trying to dig up an unexploded ordnance field. They're concerned that they've buried bombs, you can imagine, at these military sites over the years. They don't really know what's in the ground, and they'd like to dig these up. So we've replicated the controls, but put the operator off-board looking at a video screen. So we can say unmanned, but it doesn't mean that there's any real intelligence. There could be somebody driving through a video monitor or multiple video monitors, and that's what we call a teleoperation. Much more sophisticated devices do exist, although it's a little hard to tell just looking at them. What you're seeing are a couple of video clips of an autonomous vehicle that we developed, actually a student project team developed. There's some people here that were involved in that 2 years ago, called Optimus. We've developed a number of other ones before and since, but I have some nice video clips of this where it's tracking, staying between lines in the left video and in the right video, following a person around. So several different tasks that are of interest. A follow the leader type task, a road following task where the vehicle has to miss obstacles. The picture in the left, the video in the left, was an especially complex place on the course where there's a trap of barrels that drives you almost into the sideline, and so you have to be smart enough to turn back into the course. And although the video ended here, the vehicle actually made the turn. And I'm looking at the picture. Jamie, is that you in the lower right-hand corner? It might be. You probably see a lot of faces in this room in these slides, so I hope that tells you something positive. Well, there's lots of motivation for studying unmanned and autonomous vehicle systems, and especially the push towards autonomy. I think all of us would accept readily the opportunities for doing things like automated vacuum cleaning. The device on the left, a company we work with called iRobot, make a number of military products, but this is a very popular commercial product. For about $250, you can buy this little robotic vacuum cleaner. It can go under beds and under couches, and it gets stuck on a whole lot of things, and it gets confused a lot, but it's getting there. It's a pretty nice device. It actually has a base that it can go in and recharge itself when it's running low on charge. So it does have what at least we could speculate is onboard intelligence. The device on the right happens to be a version that's sold by Toro called the IMO, but the device actually is designed and built by a company also called Friendly Robotics, and that's a fully autonomous lawnmower. It also has a docking station that it can drive into, and it'll drive around your yard in kind of a triangle pattern until it cuts all the grass. But there are some real complications. You have to put a perimeter wire buried in the ground, and it has to outline everything that you want to cut. And for most of our yards, that's probably not acceptable. And it has some trouble with rough terrain and slopes. And so these are not perfect devices, but they're getting there. The Toro IMO sells for something like $700 now, so it's not unreasonable. And I think almost all of us, if there were a vacuum cleaner or a lawnmower that were not too much more expensive than what we buy now that could operate autonomously, we'd all have them. I'm pretty convinced about that. I think the real motivation, the biggest motivation, right now it's military, and a lot of our funding is from military sources. Clearly the military wants to do things like reconnaissance and surveillance autonomously. They'd like to have caravans, supply caravans, where the vehicles are fully autonomous, so we take people out of the line of fire. So that is the big motivation and the big money driving this right now. But I think motor vehicles is probably the biggest area, and there's a lot happening that you probably don't even realize. So here are some numbers that it's staggering in a way that we accept these. That last year, the latest year for statistics, 2003, the National Highway Traffic Safety Association recorded 42,643 fatalities in the U.S. It's just a staggering number, and we ought to be able to do a lot better than that. And some of the systems that are on vehicles right now, I think, are going to begin to help this situation. So everybody knows cruise control. 20 years ago, that wasn't broadly accepted. A lot of cars now are coming out with what's called adaptive cruise control, where you can put a buffer between you and the car in front of you, and if you're approaching too rapidly, the car will take the cruise control off, and then at some point even apply some braking force to try to take energy out of the car before you have an impact. So it's just fascinating what's happening. I'll talk a little bit in a minute about what we call drive-by-wire, where you're not really connected mechanically to the controls of your vehicle. Probably a lot of you are already driving cars. When you step on the gas pedal, you're not really controlling the throttle of the engine at all. You're putting input into a potentiometer, a sensor that's telling the computer in the car the desired speed, but the computer is making all the decisions about how fast to accelerate, and it does things like when the transmission goes to shift, it'll actually drop the throttle back a little bit so it feels smoother when you shift. And so a lot of things are already being taken out of your hands, and you don't realize it. I think the idea of putting a fully autonomous vehicle on the road is a bit frightening, but I think you'll see we're moving in that direction. Here's when I pulled up the Highway Traffic Safety Administration statistics. I also found this, which always surprises me, that there are more registered vehicles. There are 225 million vehicles on the road and only 194 million licensed drivers. So here's more motivation. The way I see it, there's like 31 million cars that need to be driven that we don't have anybody out there to drive. So it seems to make a lot of sense to me. I don't know. So autonomous vehicles. This is the vehicle that I showed in the video clip before. It's a vehicle called Optimus, and it's easy to see the sensors on this. There's a base vehicle. It could just as well be a Cadillac SUV that we're converting to be autonomous, or the excavator that you saw before. But here's a base vehicle that's a little more tractable for our students to work on, a little less dangerous, a little easier to find places to work. So we have a base vehicle. In this case, it's got a caster wheel in the back and differential drive wheels. So I can drive the wheel on the right and the wheel on the left independently, and therefore I can make zero radius turns, which is really nice. So this is a especially nimble mobility platform. What you don't see under the hood are all the computer systems, but you wouldn't be surprised. Many of these vehicles either use notebook computers, just like the one I'm working on here. In fact, this computer has been on one of the vehicles and running. Or it it uses a standard-looking desktop computer or something nearly equivalent to that. There are more sophisticated things, and there are small board computers, but a lot of these machines just use what you would think of as standard computer systems and electronics. What you see on this vehicle, I guess especially I wanted to point out some of the sensors, and I'll come back to this again later. This vehicle is carrying an antenna and a differential global positioning system receiver. It's got in the box that's giving it water protection, a camera for computer vision, incredible amount of sensor information coming into this system that we're processing with the computer. A little harder to see, it's got a digital compass. The GPS system gives us position very accurately, and if we're traveling at a high enough velocity, it gives us a pretty good heading, but if we're sitting stationary, it doesn't give us a heading. And so we have to know where we're headed, or otherwise when we take off, we start pointing the wrong direction. We make a lot of mistakes without a compass or some other means of getting a reference and orientation. And then finally, the device that probably people are least familiar with, but maybe in a sense the most useful for the kind of work we do, it's a scanning laser rangefinder. And so a laser rangefinder is a time-of-flight measurement of light, scanned beam of light, that the beam goes out, bounces off an object, and comes back. And based on the time of flight, we can estimate the distance to the object. We know the speed of light. And this particular device scans 180 degrees every 70 times a second. Somebody out there shake their head. About 75 times a second maximum frequency. And every half degree or so, we can pick up a distance to the nearest object. So I could have said any number if Andrew wasn't in the audience, but Andrew's sitting back there. Now I got to try to be right about stuff. It's always tough when your students are here. You can correct me on everything after the talk is over. How would that be? Okay, so I promised I would give a how-to guide. I don't know if there's anybody here that's trying to convert their own car to be autonomous, but it's 3 easy steps to convert your car to autonomous operation. We need to add actuators, so if you're going to take your passenger car and convert it, really all we're ever controlling, it's surprising if you think about it, all the complex things that we're trying to do in building an autonomous vehicle, all we're ever trying to control is speed and steering direction, either the angles of a wheel or the differential speed of tracks or wheels in a differentially driven vehicle. So it all boils down to if we can do those 2 things properly, we can exercise correct control over the vehicle. So speed and steering, but we need to automate that, and if there's no motor driving the steering wheel, we need to add a motor, and I'll show you a picture of that in a minute, and we need to add a motor to the brake and the throttle to help us control speed, and maybe some amplifiers that allow us to drive with computer voltages. We can control the motors. Then we need to add these sensors. I'll show you some more in a minute, and computers for perception, so the sensors become the eyes and the ears and maybe the touch of the robot. And we have to have memory and the ability to perform logical operations. Step 1 and 2 are pretty easy, really. We spend a lot of time in our teams doing these things, but they're the easy steps. Step 3 is really where it gets hard. Writing the software that makes the machine intelligent. And we can have some great discussions about that. But let me go through, just show you some general pictures that describe how we do these various steps. So automating the driving, creating what we say is drive-by-wire, a drive-by-wire vehicle. We need to put motors, and I haven't shown the throttle here, but it's very much like the brake. So the upper left-hand picture shows a rack and pinion steering mechanism that you would normally have in a car. And instead of having a steering wheel, or maybe in addition to having a steering wheel, we have an actuator, a motor, that can drive through a gear train and turn the steering column. And we need to have some kind of feedback on that. So it could be an encoder, or it could be a potentiometer, or other devices as well. But those are the essential elements. We have to have a drive motor, some means of powering and controlling that, with a feedback control loop. So we always have to have feedback on the system. The picture on the lower right shows one way we might implement a brake actuator, where we have a drive motor driving through a screw that could just simply be pressing on the brake pedal. Probably not the most ideal implementation, because you'd really like to have a person able to sit in the car and also press the brake pedal, so we probably wouldn't do it like this. But in concept, that shows you that it would be relatively easy to put an actuator in and actuate the brake pedal, and in the same way we could do the throttle. The motors take fairly large voltages and currents, so we don't control those usually directly from the computer. We control those through an amplifier, and the amplifier also has the provision for having feedback. So an essential element in a lot of this is an integrated or a separate amplifier that allows us to drive the motors. But the drive-by-wire conversion, again, is a pretty simple task. There are drive-by-wire vehicles. I'll show you in a little while. I know some people are here because they're real interested in the DARPA Grand Challenge. Both of our DARPA Grand Challenge vehicles have autonomous capability, but they also have the ability for the driver to get in the vehicle and just take a joystick like you would have on a computer game and do the steering and throttle, and we could also do the brake by just actuating the joystick. There's been a lot of experimental work at the car companies with drive-by-wire where instead of having a steering column, it's really fascinating to talk to the people that are in automobile safety at the car companies and begin to understand. They view the steering column as an object that you hit when you have a collision. That's their view of the steering column, and that's one of the most common sources of injuries in cars is impact with the steering column, even though they're designed to collapse. And so the idea of getting the steering column out of the car is really popular among the safety people, but when you put somebody behind the wheel, there's no wheel anymore, so that's disconcerting to drivers to climb into a car and not find a steering wheel. And then when you grab this joystick, people my age are dysfunctional. So my son, I'm sure, could climb into the car and drive no problem at all with the joystick. And so it's a generational issue also that people of my generation and older tend not to be very comfortable with the idea of climbing into a car and driving with the joystick. It really hasn't made its way into production yet. I think we may see some cars in the future that have joystick control as an intermediate step in creating autonomous solutions. I'm going to show you the sensors. This is our Grand Challenge vehicle as it looked last year. And if you don't know about the Grand Challenge, hang on a minute and I'm going to talk about that. But we need to have, so now we've given the actuating authority. We know how to act on the vehicle. We have motors that can control the functions. Now we have to give it the ability to sense the environment around it and make decisions. And so we need to put sensors on it and computers. And it's a little hard to pick out in this picture, but this is a pretty good example of where the sensors occur. So in the front of the vehicle, we have a scanning laser rangefinder just at the bumper level that really just is looking for objects. If a pedestrian walked in front of us or another car drove in front of us, that one would look almost straight out in a horizontal plane. The other two higher up are looking down, and they're trying to map the terrain in front of the vehicle. So these things are all bringing in at up to 70 or 75 times a second a full scan of how far things are in front of the vehicle in a plane. And we can use that as we drive the vehicle along to create a map. It's not perfect, but it's a pretty good sensor. We also have, again, a differential GPS receiver on top of the vehicle. That's a critical element in a lot of the work that we do. In the back of the vehicle, I don't have the hood opened up, but you just see some computers and wires and connectors and electronics in the back. So under the hood in the back, that's what replaces your mother-in-law, right? So that's the stuff in the back of the car. You don't need her in the back seat anymore. And then something you don't see at all because it's buried at about the roll center of the vehicle is the inertial navigation system. And this is a device that's incredibly complex. It's accelerometers that measure linear acceleration and gyroscopes that give us angular velocities. And based on that information, we can integrate and find our position over time. Now, those drift, and so that's what we've used to navigate for years. The inertial navigation sensors have gotten better and better, and now we can drive quite a long distance and maintain a pretty accurate path just using the inertial navigation sensors. But we also now have the GPS system that we can read our positions fairly accurately. We have systems that operate somewhere in the order of 10 centimeters pretty consistently. So the first two steps, I would say, automating the car by putting motors for the drive and steering, the throttle, brake, and steering. That's easy. Adding the sensors, computer vision systems are very well developed at this point. Lots of information coming in. The laser rangefinders, GPS, inertial systems, all those are pretty well developed. We can certainly improve, but at this point, they're pretty reliable pieces of equipment that give a lot of good data. The real tough problem is step 3. So I would say we've basically solved, not completely, but in a reasonable way, the first 2 steps. Now we've got to figure out how to give this thing intelligence. What kind of software do we put in the computer that allows it to be able to give you the same instructions that your mother-in-law gives you, or to actually drive the vehicle on its own. And we could talk, again, all day. We had a great discussion in class yesterday about just some basic ideas about reactive behavior versus behavior that has more thought behind it. But I would divide, not everybody would agree with this, but I would divide the strategies for navigating into 2 broad classes. One is what we call behavior-based, where you're simply looking at the external environment. You're not trying to create a map or build on a map. You're just reacting to the things that are there. You're saying, let's follow a road if it's there. We need to follow GPS waypoints. We don't want to run into anything. That's relatively simple to program, but it also has shortcomings too. It doesn't give us a global picture of where we're trying to go in the world. The map-based approaches, we would create a detailed map. GIS, there's a lot of data out there for what the terrain looks like, what kind of land cover, where the streams are, where roads are, where bridges are. So there's a lot of data that's already available in maps, and then our sensors aboard the vehicle can collect additional information and allow us to refine those maps. And then we need to have a strategy for driving through, and so we call it those lowest cost algorithms, trying to find the path, in essence, of least resistance, where we're not going up too steep a hill and we're not running into anything. So I would broadly say we have behavior-based approaches and map-based approaches. I'm not going to talk any more about that, but I'd love to have discussions. I know I will with the students after we get finished here. But I wanted to spend a little bit of time talking about our student projects. And we do so many of these, and we do so well in the competitions, and I'm really proud of what the students do. So just to say that they're all team-oriented, based on competitions. They directly support our research, and in fact, almost all the graduate students that work with me were involved in these as undergraduates, and there's still a lot of interaction back and forth. If you've never been to the WARE Lab, you really should go. That's, to me, the best place on campus. Here are the students, not all of them, but this is a subset of the students that are working with me this semester. There are some graduate students mixed in here, but mostly these are the students involved in 5 different undergraduate teams, and I'm going to go quickly through the 5 things that we're doing. This is something we've done well at for many years. I don't know if you can see the check, but last year we won the $10,000 grand prize in the Intelligent Ground Vehicle competition. You see the team, and if you look back in the audience, you'll see a lot of the students in this picture were undergraduates last year that are graduate students this year. So this is the Intelligent Ground Vehicle competition, building small robots to navigate in an outdoor road-type environment. We also have an autonomous aerial vehicle team that's got 2 subparts. We're doing a rotary wing competition called the International Aerial Robotics Competition, where we have to find waypoints first, and then we have to locate a building that has a picture drawn on it, and then ultimately we have to find an open window and stick a camera in the window and take a picture of what's inside there. Really challenging competition. There's also a fixed wing competition where we have to just do surveillance, fly over waypoints and take pictures. So we've got vehicles for both, and we've got a student team that's kind of divided up and working on both of those problems. We also have a team that's working on a high-speed autonomous vehicle. We think there's a lot of opportunity to do things like stability testing for the car companies, and so GM donated this Cadillac SRX to us. It's sitting out at a lab at the airport, and our goal is to take it to the track, the Virginia International Raceway track in Danville, and hit the 100-mile-an-hour barrier. Now, I don't know if we can do that this year. We're struggling a little bit, but that's the goal, and that's a goal I set. I'm not sure it's a hard and fast goal, but once we can drive at high speeds autonomously, we can begin to test things that you can't do with a test driver. You don't want to do things like at very high speeds blow a tire out, but if we have an autonomous vehicle, we can begin to test those kinds of reactions. And if you don't know it, a lot of cars now have stability control systems, so you may think you're driving, but there's a lot that's going on under the hood, decisions that are being made for you. Your car, if you have stability control, your car is deciding to apply brakes or throttle at some point in time. It's probably going to change suspension characteristics and maybe even enact steering behavior to try to keep you from rolling your car over or getting into an accident. You're not fully in control anymore. Probably the most exciting project, or at least to the outside world, they're all pretty exciting to me, but the DARPA Grand Challenge. Last year we entered. There's another race coming up. Nobody won last year. October 8th of this year, we have a team that's vigorously working on 2 vehicles. It's a cross-country, cross the Mojave Desert race. Last year it was about 150 miles of open desert terrain, 10 hours to finish. If you beat everybody else and you finish in under 10 hours, you win $2 million. So I'll have to send my deposit slip to them, so that's what I had to do last year in case we won. They could deposit $1 million. Last year was $1 million, so I was holding out really for the $2 million prize. Here's the vehicle we entered. You already saw a picture of this. That's it at the California Motor Speedway. And here we are in qualifying. Last year there were 106 teams that entered, and there were 25. DARPA evaluated all our technical reports and in many cases did site visits. We qualified without that, but came to site in many cases and invited what they thought were the top 25 teams out to the California Motor Speedway. And the videos here are of the California Motor Speedway pre-qualifying We were one of only 7 teams to complete the course out of the 106 that started, and we were seeded 5th overall. The day of the race, we went about 100 yards, and we put our own brakes on by a software error, and that's pretty easy to do. You only got one chance. So we didn't do as well as we would have liked, but we're back again and gunning for the 2 million. So here's the team out at California Motor Speedway. I also wanted to mention something that I think is great. We're heavily involved, and a lot of the students here are heavily involved in First Lego League. And this is a 9 to 14-year-old competition to design and build autonomous vehicles. This is where the talent's coming from, and so we're supporting this pretty heavily too. Last year, just to mention, the numbers are up there, but last year we had about 1,600 students in 9 regional tournaments, and about 600 students came to Blacksburg to compete in this. And that was a video I shot in Blacksburg. And I should give credit to Bill Duggins and Susan Bright, who were really the leaders of the First Lego League competition. There are so many unsolved problems. I sat in a couple minutes, I jotted a bunch of things down, and I just didn't want to copiously list everything on slides, but I think any field of endeavor just about would find ways to relate to the problems of designing autonomous vehicle systems. There are so many unsolved problems in mathematics and operations research, the algorithms, things like the traveling salesman algorithm. That's not quite what we solve typically, but those kinds of problems of trying to find the shortest way to get from, or the least resistance way to get from one place to another. How do you represent knowledge in the computer, and how do you categorize and classify it? In biology and behavioral sciences, really fascinating questions like cognition. How can I look at somebody who's very far away and has their face covered, and just perhaps by the way they move or some slight nuance, I can identify the person? And how do we give a computer or an autonomous vehicle that kind of cognitive ability to assemble all these visual or sensory cues and put them together and somehow make sense out of them? And there are a lot of unanswered questions about how biological systems do these things. When do we put things in short-term memory, and when do we put them in long-term? There's lots of interest. We have in our Grand Challenge vehicle, last year we had 5 computers. Did we end up with 5? Andrew's shaking his head. 5, and so we do a lot of parallel processing. Probably didn't make as best use as we could of those, but interest in parallel processing, and obviously that means networking. In engineering, there are just endless problems. We can still improve these sensors, control systems, systems integration. I put safety on here because I always tell the students that you shouldn't leave safety off your list, so they all have heard this from me over and over again. We work pretty closely with Bill Karstensen, for example, in geography, developing the maps and the paths through the terrain, for example, in the Grand Challenge. Here's one of my all-time favorite Far Side cartoons, so I just couldn't resist it. It just isn't as easy as you think. You know, how do you get, that's the bottom line question. So all these other problems are small in comparison to the fundamental question, how do you get from point B to point A? I really like our university motto, and I think it's pretty symptomatic of the work that we do, at least. And I know maybe it doesn't fit everybody as well, but I like the idea that we're developing new knowledge, but we're also really committed to putting the knowledge that we're developing into practice and working with the students to do that. Thanks for your attention today, and thanks for the great turnout. I'm really surprised. I honestly expected 1 or 2 people here, and I thought we could just sit up here and I'd put my computer on my lap and we go through this together. So thank you for attending today, and I'm happy to answer any questions.